Welcome to the deep dive. If our last journey was all about getting clean water to your tap, today we're diving into its equally crucial yet often unseen mirror image.
That's right.
We're going to explore what happens to water after you've used it. Think of it as the other side of the water coin, wastewater treatment. One system makes natural water safe to drink. The other cleans our used water so it can safely return to nature.
Exactly.
Our mission today is to follow that entire hidden journey from your drain all the way to its final return to the environment. And this isn't just, pipes and pumps. It's really about public health, environmental stewardship, and a cycle that impacts every living thing.
It's truly fascinating how distinct yet profoundly complementary these two halves of the water cycle are.
Yeah.
We'll be looking at, everything from the plumbing under your house to the really advanced technologies that protect our planet.
Okay.
Our goal is to sort of peel back the layers of complex engineering and microbiology that truly make modern civilization possible.
So let's start with that fundamental difference then. You drink water that's gone through a really rigorous cleaning process. But what about the water you've used? What's the biggest contrast between the water entering a drinking water plant versus, say, a wastewater treatment plant?
Oh, it's a night and day difference.
Yeah.
Really. Drinking water typically starts as relatively clean natural water from rivers, lakes, or underground aquifers. It might have some sediment, maybe some naturally occurring microbes, but that's about it.
Okay.
But wastewater, that input is just this complex cocktail from homes, industries, even storm runoff sometimes.
Yeah.
We're talking human waste, cooking grease, soaps, industrial chemicals, microplastics, you name it.
Right.
It's often very high in organic matter and pathogens, and frankly, it looks and smells quite foul.
And the output has completely different goals too, right? Drinking water has to be absolutely pristine, meeting strict EPA standards for us to consume safely. What about the water leaving a wastewater plant?
Exactly. The treated water, or effluent, from a wastewater plant doesn't need to be drinking water quality unless it's specifically being reused for that purpose, which is becoming more common, but isn't the primary goal everywhere.
Ah, okay.
Its main goal is to be clean enough to safely rejoin a river, lake, or ocean without harming the aquatic ecosystems there. That's regulated by permits under the Clean Water Act.
So it's like TIFE.
So if drinking water treatment is about protecting people from what nature might have left behind, wastewater treatment is really about protecting nature from what we leave behind.
That makes sense. Trust versus responsibility.
Precisely. It boils down to trust at the faucet and responsibility at the river. Together, these two processes form this essential loop that allows us, civilization, to use water continually without poisoning our environment.
That's a powerful way to put it. Now, with such varied stuff coming in, I imagine there isn't just one single universal way to treat all this wastewater, is there? What kind of different systems are actually out there?
You're absolutely right. The diversity in wastewater treatment plants it's a direct response to local needs, population size, geography, environmental regulations, and of course, budget.
Right.
For example, in rural areas, you often find septic systems, pretty common. These are decentralized, usually just a buried tank that settles out the solids, and then the liquid, the effluent, seeps into a drain field where the soil itself naturally filters it.
Okay. Simple enough.
Yeah, they're cost-effective for individual homes, but they do require careful maintenance. You can't just ignore them.
And as communities get bigger, the solutions have to scale up, I assume.
Precisely. For small towns or maybe specific industrial sites, you might see stabilization ponds or lagoons. Think large, shallow ponds where natural processes, sunlight, oxygen, microbes, do the work of breaking down waste.
So it's eco-friendly.
They're low energy, which is great,
Yeah.
but they need a lot of land, and sometimes they can have odor issues. Then, for most cities and larger towns, the real workhorse is the conventional activated sludge plant.
That sounds familiar.
Yeah, these are highly effective. These big aeration tanks where air is bubbled through the wastewater. This supercharges the naturally occurring microbes, which then digest the organic matter much faster. They're efficient, but they do use quite a bit of energy and need skilled operators.
Okay. And what about places with, really tight space constraints? Or maybe places trying hard to reuse water?
Ah, good question. That's where you start seeing more advanced systems like membrane bioreactors, or MBRs.
MBRs.
Yeah, membrane bioreactors. They basically combine that activated sludge process with advanced membrane filtration. Think of superfine filters. They produce incredibly clean effluent, often clean enough for reuse. They do it in a much smaller footprint than conventional plants. They're more expensive, though, both to build and operate, but ideal for dense urban areas or, like you said, regions really focused on water reuse.
And then the top tier.
And then for the most sensitive environments, or if you're aiming for direct potable reuse, actually turning wastewater back into drinking water, we employ advanced or tertiary treatment. This adds even more steps, like nutrient removal for nitrogen and phosphorus, maybe reverse osmosis, UV disinfection, ozone.
Yeah.
It produces water that's almost distilled quality. It's a monumental engineering feat, but very high energy, very high cost.
So many options.
So what's fascinating here is that each solution isn't just a technological choice. It's really a testament to human ingenuity, adapting to local constraints, and also, our evolving commitment to protecting the environment downstream.
From a farmhouse septic tank to a megacity MBR plant, it reflects where we live and how much we invest.
That makes perfect sense. So the system has to adapt to what's coming down the pipes. Let's unpack that a bit. What are the main categories of wastewater that these plants are designed to handle?
Broadly speaking, you can think of three main types. First, there's residential or domestic sewage. This is pretty consistent stuff. Human waste, water from kitchens, laundries, showers.
Okay, predictable. Right. It's high in organic matter and pathogens, but generally predictable in volume and composition. Standard biological treatment, like activated sludge, handles this pretty well. The main challenge is just the sheer consistent volume.
And then things get more complicated, I imagine, with industrial wastewater.
Oh, much more so. Industrial wastewater is incredibly varied. Depends entirely on the industry. A brewery, for example, will have really high organic loads. A metal plating factory might discharge heavy metals or have big pH swings. A textile plant could have dyes and specific chemicals.
So you can't just dump that into the city sewer?
Often, no. It frequently requires highly specialized pre-treatment on-site at the industrial facility before it even enters the municipal sewer. Because many industrial chemicals can be toxic, they can literally poison the beneficial microbes that the whole municipal plant relies on. Kill those off, and the plant stops working.
Right. And the third category you mentioned, stormwater, that has its own set of problems, doesn't it?
Absolutely. Stormwater runoff, especially in older cities where it might mix with sanitary sewers in what's called a combined system, is a huge challenge. Rainwater flowing over streets picks up everything: oils, trash, fertilizers, road salts, pet waste. When this surges into treatment plants during a heavy rain, it can completely overwhelm their capacity. This can lead to overflows of untreated sewage directly into rivers or lakes. Not good.
Yeah, I've heard about those CSO events.
Combined sewer overflows, exactly. Even in systems where storm and sanitary sewers are separate, sometimes rainwater gets in through cracks or bad connections. It's called inflow and infiltration, or INI. This extra water dilutes the wastewater, which actually makes it harder for those delicate microbial communities to treat the sewage effectively.
So too much water is almost as bad as too little.
In a way, yes.
Right.
It really highlights how sensitive these treatment plants are. They're essentially living systems, and the microbes thrive on a relatively consistent diet. Sudden changes in flow, pH, temperature, or unexpected toxic inputs can crash the entire process for days or even weeks.
You mentioned things that can poison the microbes or cause other problems. What are some of those notorious things people send down the drain without thinking?
Oh, the list is unfortunately long. But some major culprits, the ones that cause the most trouble. Number one is probably grease and fats. Cooking oils, fats poured down the sink, they solidify in the cool pipes.
Right.
They cling to the pipe walls and combine with other debris, especially wipes, to form these massive blockages. We sometimes call them fat bergs.
Bergs, I've read about those, like in London.
Exactly. They can weigh tons, literally tons, and cost cities millions of dollars to break up and remove. Then you have wipes and trash, even the ones labeled flushable. They just don't break down like toilet paper.
So flushable doesn't mean sewer friendly.
Not at all. They are a major cause of clogged pumps, tangled screens of the treatment plant, a huge operational headache. Then there are toxins and harsh chemicals, maybe from household cleaners, pesticides, or industrial spills. These are silent killers for the beneficial microbes.
And what about things like medicines?
Yeah, pharmaceuticals are another growing concern. While usually in smaller concentrations, many are difficult for conventional treatment plants to remove completely. So traces can end up in our rivers and potentially affect aquatic life. It's just a clear reminder that our drains aren't magic portals, Everything we send down eventually goes somewhere, and often it ends up making the job of these vital, unsung systems incredibly difficult.
That's a powerful point. Okay, so with all this diverse and sometimes really problematic waste, how does it actually travel from our homes and businesses to the treatment plant. It's not always just a straight shot downhill, is it?
No, rarely is, especially in larger areas. The primary method is gravity flow. Pipes are carefully laid at a slight downward slope, maybe just a quarter-inch drop per foot. It's the cheapest, most energy-efficient way to move wastewater.
But cities aren't always built on convenient downhill slopes. What happens when you have hills or just really flat areas where gravity isn't enough?
Right, exactly. That's where sewer pump stations, often called lift stations, become absolutely indispensable. These are essentially underground collection pits called wet wells, where wastewater from a neighborhood or area gathers by gravity.
Okay.
When the water level in the wet well rises to a certain point, sensors trigger powerful pumps. These pumps kick on and push the sewage uphill or across flat ground through a pressurized pipe called a force main.
A force main. Got it.
Once the sewage reaches a higher elevation manhole or another gravity line, gravity can take over again. A large city might have dozens, even hundreds of these lift stations scattered throughout its network.
So these pump stations are really like the hidden heartbeats moving those shadow rivers of wastewater you mentioned earlier. What are the major challenges of keeping these critical transport systems running smoothly?
Oh, they face constant battles. Power outages are a huge concern. If the power goes out and the pumps stop,
Sewage backs up.
sewage backs up quickly, potentially into homes or overflowing onto streets. That's why reliable backup generators and automatic transfer switches are absolutely essential for every single lift station. They have to kick on instantly.
Makes sense.
They also deal with really harsh conditions. Corrosion is a big one. Hydrogen sulfide gas, which is a natural byproduct of sewage decomposition, is highly corrosive to concrete and metal components inside the wet well and the station itself.
Nasty stuff.
And of course, blockages are a constant threat. Wipes, grease, grit, random debris, all can clog pumps or pipes. So maintaining this vast hidden network beneath our feet requires enormous ongoing effort and continuous monitoring. Every single one of these stations is a potential failure point, and ensuring their reliability 24/7 is a monumental task for utility crews.
Speaking of blockages, that's where things can get really messy, not just for the utility, but for homeowners too, right? What happens when a sewer pipe gets clogged, especially one deep underground?
Yeah, blockages are a major headache all around. As we discussed, crease buildup and those infamous wipes are big culprits. But you also get tree roots actively growing into pipes seeking water, or simply pipes collapsing due to age or ground shifting. Sediment can build up too.
And the result is?
The result is sewage backing up. It can back up into basements, overflow from manholes into streets, maybe even pollute nearby streams. Plus, blockages put a huge strain on those upstream pump stations.
So how do crews deal with that? Do they have to dig?
Not always, thankfully. Maintenance crews have specialized equipment. They often use powerful jetting trucks that blast high-pressure water down the pipe from a manhole to break up blockages. Or they use vacuum trucks, often called vac trucks, which have powerful suction hoses to pull out debris, sludge, and water from manholes or wet wells.
Okay, jetting and vacuuming. But what if the pipe itself is actually broken or collapsed? That sounds like a much bigger, more expensive problem, especially if it's under a busy road.
It absolutely can be. Often, crews can still access the sewer system through manholes. You see those round covers everywhere on streets. They're usually spaced every 300 to 500 feet, allowing access for inspection, cleaning, and repairs.
So they send cameras down.
Exactly. They use CCTV cameras mounted on robotic crawlers to go down the manhole and travel through the pipe to inspect its condition and pinpoint problems remotely. If a repair is needed, sometimes they can use amazing trenchless methods.
Trenchless, meaning no digging.
Right. Methods like cured-in-place pipe or CIPP lining. They basically insert a flexible resin-saturated tube into the old damaged pipe, inflate it and then cure it using hot water, steam, or UV light. It hardens to form a brand new seamless pipe inside the old one.
Wow, like surgery for sewers.
Kind of, yeah. Or there's slip lining, where they pull a slightly smaller new pipe segment through the existing damaged one. These trenchless technologies are fantastic because they avoid the massive disruption and cost of digging up roads, sidewalks, and everything else.
So you're saying they don't always have to bring out the backhoes and shut down the street for weeks. That's really good news.
Exactly. Trenchless methods are far less disruptive, usually faster, and often less expensive overall than traditional excavation, where you have to dig a big trench, replace the pipe section by section, backfill, and then restore the road surface.
But digging is still sometimes necessary.
Unfortunately, yes. Sometimes the pipe is too collapsed or there are other complications. And excavation is very expensive. We're talking potentially hundreds of dollars, maybe even over $1,000 per foot of pipe replaced under a major road. A single block-long repair could easily run into hundreds of thousands of dollars.
Ooh, why so costly?
Well, think about it. Those sewer pipes are buried deep, often sharing crowded underground space with water lines, gas lines, electric conduits, fiber optic cables. Digging is complex and risky. You need specialized crews, heavy equipment, traffic control, road closures, and then full restoration afterwards. Plus, in many older cities, particularly in the U.S., we're dealing with infrastructure pipes that could be 50, 75, even 100 years old. They're reaching the end of their lifespan. Maintaining this hidden city is just an ongoing, massive investment.
And who pays for all this? If it's the main sewer line under the street.
If it's the public sewer main, the cost is typically borne by the local utility or the city, funded through your sewer bills or sometimes taxes. But here's a key point for homeowners. The pipe that runs from your house out to connect to that public main in the street, that's called the private sewer lateral.
The lateral.
Right. And in most places, the homeowner is responsible for maintaining and repairing their own lateral line, all the way to the property line, or sometimes even to the main sewer itself, a blockage or break in your lateral. That repair bill is usually on you.
Ouch. Good to know. Maybe explains those sewer line insurance offers you sometimes see.
It does. It can be an unexpected and costly repair for homeowners.
Okay, fascinating. So we've traced the journey of the wastewater, the challenges of moving it through pipes and pumps, and the headaches of fixing blockages. Let's quickly recap what happens once it finally arrives at the treatment plant, especially what happens to all that stuff that gets removed, the solids, the grit, the things that can't just be treated and released as clean water.
Right, good point. The journey isn't quite over even at the plant gate. It typically begins with primary treatment, which is mostly a physical process. First, it goes through large screens or bars to catch big items, rags, wipes, sticks, whatever people flushed or got into the system.
Stuff you don't want hitting the pumps.
Exactly. Then it flows into grit chambers, which are designed to slow the flow down just enough so that heavy inorganic materials like sand, gravel, and eggshells settle out. This protects downstream equipment from abrasion. After that, the water goes into large primary settling tanks, or clarifiers. Here, the water sits relatively still for a few hours.
Letting gravity do the work again.
Precisely. Heavier organic solids sink to the bottom as primary sludge, while lighter materials like grease and oils float to the top as scum, which is skimmed off. This whole primary stage removes maybe 50 to 60% of the suspended solids and a good chunk of the organic load.
Okay, so that handles the big stuff and the easy to settle stuff, and then comes the crucial biological stage, right? The microbes get involved.
Yes, secondary treatment is really the biological heart of most municipal wastewater treatment processes. The water, now with much less solid material, flows into aeration tanks. This is where, as we mentioned, billions of beneficial microbes, bacteria, protozoa get to work. Air is actively pumped in to provide oxygen, which these microbes need to thrive and rapidly consume the dissolved and fine suspended organic matter remaining in the water, essentially their food.
They're basically eating the pollution.
In essence, yes. After they've feasted in the aeration tanks, the mixture of water and microbes flows into secondary clarifiers. These are similar to the primary settling tanks. Here, the now heavier clumps of microbes, called activated sludge, settle out, leaving much cleaner water, the secondary effluent, on top. A portion of that settle activated sludge is actually returned to the aeration tanks to keep the microbial population high and hungry.
Recycling the workers.
Exactly. This is where those sensitive microbial communities we talked about earlier are absolutely vital. Keeping them healthy and active is key to the whole process. And then, for situations requiring even cleaner water, you have tertiary treatment.
The final polish.
Right. This is an additional stage, or stages, after secondary treatment. It's designed to remove specific things that might still be left, like nutrients, nitrogen, and phosphorus, which can cause algae blooms in rivers. Or it might involve fine filtration through sand or membranes, or disinfection using UV light or ozone to kill remaining pathogens, especially if the water is being discharged into sensitive waters or planned for reuse.
So after all that cleaning of the water, what about the actual physical stuff that's collected throughout the process? The grit from the chambers, the scum skimmed off the top, and all that sludge that settles out? Where does that go? It doesn't just disappear, right?
That's a very good question, because it absolutely doesn't just disappear. Managing these residuals is a huge part of wastewater treatment. The screenings and grit collected right at the beginning, that's typically washed to remove organics and then sent to a landfill. It's mostly inert material.
Okay.
The primary sludge and the excess activated sludge from the secondary clarifiers, this combined material, is often just called sludge, or more technically, biosolids after it's been treated. Treating the sludge is a whole process in itself.
What does that involve?
Often it involves anaerobic digestion. Sludge is put into large, sealed tanks without oxygen, where different kinds of microbes break it down further. A major byproduct of this is biogas, which is mostly methane.
Methane. Can they use that?
Yes. Many larger plants capture this biogas and use it as fuel to generate heat or electricity, often powering a significant portion of the treatment plant itself. It's a great example of resource recovery.
Turning waste into energy. Cool.
After digestion, the remaining biosolids are dewatered to reduce volume. Depending on its quality, there are strict regulations about pathogen levels and contaminants like heavy metals. These treated biosolids can have several fates. If they meet the highest standards, they can be applied to agricultural land as a fertilizer and soil conditioner. It's rich in nutrients.
Closing the loop.
Exactly. If it doesn't meet those standards, or if land application isn't feasible locally, it might be incinerated, with the ash landfilled, or just sent directly to a landfill. So while the water gets cleaned and returned to the environment, the solids that are removed are carefully managed through these various pathways, aiming for either beneficial reuse or safe disposal.
This brings us perfectly to a classic pop culture line that I think almost everyone knows or thinks they know, Finding Nemo.
Ah, yes.
And that famous phrase the fish keep saying, all drains lead to the ocean. Based on everything we've discussed, how accurate is that really?
It's a great line for a kid's movie, definitely memorable. But in reality, it's a bit of a myth versus reality situation. And if we connect this to the bigger picture, understanding the difference is actually crucial.
Okay, so break it down for us.
Okay. Storm drains those grates you see along curbs on the street, designed to collect rainwater runoff. In most modern systems, those often do discharge directly into the nearest river, lake, or sometimes the ocean, completely untreated.
Untreated, really?
Yes. The idea is just to get rainwater off the streets quickly to prevent flooding. This is why you should never dump oil, paint, chemicals, or anything else down a storm drain. It goes straight into the local waterway, pollution and all.
Okay, that's important. But what about the drains inside our houses? Toilets, sinks, showers.
Those are connected to the sanitary sewer system. And sanitary sewers, in almost all developed areas, lead directly to a wastewater treatment plant first. The water goes through all the primary, secondary, sometimes tertiary treatment processes we just talked about before it's discharged back into the environment.
So Nemo's escape route, not so realistic.
Let's just say if Nemo had actually gone down that dentist's sink drain into the sanitary sewer, his journey would have involved navigating screens, grit chambers, swirling aeration tanks full of hungry microbes, settling tanks, possibly disinfection. His chances of survival and popping out happily in Sydney Harbor would be highly improbable, let's put it that way.
Yeah. Okay, so no easy ride to the ocean via the toilet. But the line still serves a purpose, maybe? It gets people thinking.
It absolutely does. In a broader sense, it highlights a fundamental truth. All water is ultimately connected. What we put down any drain, whether it's a storm drain or a sanitary sewer, does eventually make its way back to the natural environment. The critical difference is whether it gets there directly and potentially full of pollutants, or whether it goes through that complex, vital cleaning process first.
Right.
So the real story isn't simply that all drains lead to the ocean. It's really about how we care for the water, how we manage that journey before it ultimately rejoins the natural world.
That's a perfect way to put it. This whole deep dive has really, truly unveiled the incredible complexity, the immense cost, and the constant, often invisible care that goes into managing our used water. From the smallest backyard septic tank to these vast, hidden under-the-city networks of pipes and pump stations, and then onto those sophisticated treatment plants. It's just a silent, constant battle against gravity, against waste, and against the sheer volume of everything we discard.
It really is.
It truly drives home that point about our collective responsibility to nature, responsibility to future generations who relied on the same water.
Indeed. All water eventually finds its way back to nature.
Sure.
That's inevitable. The real question, the one we have control over, is in what condition does it arrive?
Right.
So maybe a final thought for everyone listening. Next time you flush a toilet, run the laundry, or even just watch rain disappear down a storm drain on the street, take just a moment. Consider that invisible, complex journey that water is about to take. Think about the hidden systems and the people working tirelessly to manage it. And maybe ask yourself, what role do you play in its ultimate destination and its condition? What single small change could you perhaps make to lighten the load on this vital hidden system that supports us all?